In this video, I will talk about kinematics, and then we will solve practice problems that will help you to understand the concept. Kinematics is a branch of physics that studies motion without considering the forces that causes the motion. Net external forces cause motion according to Newton's first law of motion. In kinematics, motions are described by distance, velocity, speed, and acceleration. Let's say you move from point A to point B. Point A, if this is point A, it should be noted that motion is always with respect to a point. So let's say that you are on the XY coordinate system, where this is the x-axis and this is the y-axis. Point A, let's say point A is at point x1 and point y1, and then point B is at point x2 and point y1. The distance from point A to point B is what we want to look for. Let's say it is D. Okay, if this is y2, then this is y1. So in order to find the distance, we can find the distance using the Pythagorean theorem, since it forms a right angle triangle. Pythagorean theorem is hypotenuse squared. The hypotenuse is the longest side, which is d, that is d squared, is equal to the sum of the squares of the other side, which is the adjacent square. The adjacent in this case is x2 minus x1, which is this place. Let's call it L. So let's say x2 minus x1, then square, plus the other one, which is y2 minus y1. Let's call it h. So that will be y2 minus y1. So okay, now the distance from point A to B is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So this is the amount, that is the magnitude of your change in motion. The magnitude of the change in motion. How much did a body change from point A to point B? This is the amount. As a result, the distance of an object is the magnitude of its change in motion. That is how much you have traveled from one point to another. Now let's define displacement. Displacement is the distance moved in a specific direction. That is, it will talk about the magnitude and it will talk about the direction. Distance talks about only magnitude, the amount, but displacement talks about the amount of travel, and the direction of travel. So let's say this is your amount of travel. This is your amount of travel. Then in what direction? Is it due north? Okay, so this amount of travel due north gives you displacement. So the difference between displacement and distance is that distance is a scalar quantity, that is, it deals with only magnitude, that is the amount of travel, and then displacement is a vector quantity because it deals with the amount of travel and the direction of travel. Now let's solve this practice problem. If a player runs from his own goal post to another team goal post and then back to his own goal post, what is the displacement of the player? Now, displacement is a vector quantity. Now, let's say that this is the goal post and then this is the second goal post. A player runs from this point now, then he returned to his goal post. Okay, if a player runs from his own goalpost to another goalpost and then back to his own goalpost, what is the displacement? So the player left from this point to this point and eventually he returned to this point. Talking about displacement, he has not moved at all. If the distance between the two goalposts is 100 meters, he had covered, and this is another 100 meter. Although he covered 200 meters, his distance is 200 meter, but the displacement, which is a vector quantity, but the displacement is equal to 0, because with it, with respect to direction, it has a magnitude of 200 meter, but in what direction? In no direction, because this man is actually at his own goalpost. So if he had moved from this point to this point, the distance would have been 100 meters, probably towards the positive x-axis or towards the east. That would have been the answer. But because he returned to his own goalpost, his original position, so in that position there is no direction. It's, if somebody, it will look to another observer like he had not moved at all. The displacement is 0 meter, while the distance is 200 meter, because he had actually, the amount of his travel is 200 meter. So speed is the time rate of change of distance covered by a body. That is, speed is the time rate of change of distance that is covered by a particular body, while velocity is the time rate of change of displacement covered by a body. Speed is a scalar quantity, while velocity is a vector quantity. Speed gives only the magnitude of how much distance changed with time, while velocity gives the amount of distance that changes in time with a particular direction. So let's say that a bicycle moves in this direction, moves in this direction at the speed of 20 kilometer per hour. This is the speed of that bicycle, but the velocity of the bicycle is 20 kilometer per hour towards the east or due east. Let's say that a bicycle rider, he rides a bicycle from this point back to this point at probably 20 kilometer per hour. This is the speed of the bicycle, but the velocity of that bicycle is 0, because just like the former example, he had not moved at all with respect to an observer, because he is back to his original position. Direction is 0. So if direction is 0, then there is no velocity. So velocity is a vector quantity. It considers the direction of an object, while speed only considers the amount, which is just 20 kilometer per hour. Let's talk about average velocity and instantaneous velocity. Instantaneous velocity is the velocity of an object at a particular instant. Let's say that a bicycle rider rides bicycle in this direction, in this direction. At every point, he has a particular speed. The speed changes at every point because he accelerates. He accelerates in different directions. The speed or the velocity at a particular instant and at a very small interval of time is referred to as instantaneous velocity or instantaneous speed. Instantaneous velocity is the velocity at a particular instant, while instantaneous speed is the speed at a particular instant. As a result, the instantaneous speed of an object is the time rate of change of distance, but because it is at a particular instant of which the time tends to 0, so it is referred to as the limiting value. That is, it is the limiting value of the rate of change of distance when the change in time is very, very small. That is, when the change in time tends to 0, it is very, very small. The time interval is very, very small. The change in time tends to 0. So we, at that point is where we are looking for the rate of change of the distance. So this is the formula to find the instantaneous speed. For instantaneous velocity, it is the rate, it is the limiting value of the rate of change of displacement when the time approaches zero, or when the time is very, very small. And this is the expression for that statement, the limiting value. So at every point, the speed at every point, at every instant, the time is very, very small at this point, and that's why we say that the change in time approaches zero at that point. Now, how about average speed and average velocity? Average speed is the total distance covered upon the total time. Now, when we are considering average, it is simply talking about the total movement. It is simply the consideration of the total movement. In that case, the details of the speed at each point is not being considered. If we want to consider the speed, general speed, it's just like the speed at every point is not constant. So because it increases at every point, and as a result, the average speed will now be equal to the total distance upon the total time. That is the total distance covered upon the total time taken. Okay, the same thing with average velocity. Average velocity. That means average velocity will be total displacement upon the total time. When driving a Toyota Avensis car along a straight road for 16.5 km at 50 km per hour, it suddenly runs out of fuel and stopped. Over the next 20 minutes, you walked another 2.5 km further along the road for a petrol station. Determine the average velocity of your journey from beginning of your drive to your arrival at the fueling station. Okay, so the the road is 16.5 kilometer. Okay, you drive your car along a road for 16.5 kilometer. Okay, let's say the distance from this point to this point, let's say this is 16.5 kilometer. Let's say that is d1. Okay, and you, along that distance, you drove with the velocity of 50 kilometer per hour. So let's say that is v1. Okay, now it suddenly runs out of fuel at this point, at this junction. Okay, now, and stopped over the next 20 minutes. That is, for the next 20 minutes after this point upward, for about 20 minutes, let's say that is t2. For about 20 minutes, you walked another 2.5 kilometer, that is d2. So this line is 2.5 kilometer d2, and this is t2, 20 minutes. Okay, and then this is v1, your velocity for the first 16.5 kilometer per kilometer. Okay, now further along the road for a petrol station, determine the average velocity of your journey from the beginning of your drive to your arrival at the fueling station. So we want to find the average velocity from this point to this point. I told you average velocity is about the total displacement and the total time taken. We are not, in this case, we are not concerned about the instantaneous velocity, the velocity of your car at every instant. We are concerned with the overall velocity. Now, the average velocity is equal to the total displacement, okay, upon the total time. The total displacement in this case, that will be d1 plus d2. That is the distance covered on this red line and the distance covered on this place as well. So, and then the total time, that should be t1 plus t2. We know the value of t2, which is this, and that's, of course, that is 20 minutes. Okay, and then but we don't know the time spent for the first 16.5 kilometer. Let's say that is T1. Now let's find, since we already know D1, D2, we need to find T1 since we already know T2. Now let's find T1. To know T1, then we need to make use of the parameters for the first 16.5 kilometer. Since velocity is displacement upon the time, so we can say displacement. So V1 is equal to D1 upon T1. So it implies that T1 is equal to D1 upon V1. The D1 in this case is 16.5 kilometer, and then the velocity at that distance or at that displacement is 50 kilometer per hour. So kilometer cancels kilometer, so that I will have 16.5 divided by 50. Okay, on my calculator, that's 0.33 per hour. 0.33 hour. All right, but don't forget that this time is in minutes, so we may decide, we may convert it to hours as well. If we convert it to hours, so that everything will be in kilometer per hour. Now let's convert 20 meters to hour. That's 20 divided by 60 in hour. Okay, so we'll have something of this nature: 20 divided by 60, which is also 0.33 hour. As a result, we'll have something of this nature: D1 plus D2, that is 2.5 plus 16.5 kilometer, so that is 19 kilometer. So that's 19 kilometer upon T1 plus T2, that's 0.33 plus 0.33, which is 0.66 hour. So in this case, we have 19 divided by 0.66, which is equal to 28.78 or 28.79 by approximation in kilometer per hour. Oh, this is hour. Okay, so all right, so in order to convert this to seconds, we can have 28.79 multiplied by 10 raised to power 3 upon meter. Since kilo means 10 raised to power 3, then we'll be left with meter, then divided by hour, and 1 hour is 3600 seconds. So we'll have seconds here. As a result, then we'll have 28.79 divided by 3. Okay, 28.79 exponential 3, okay, divided by 3600, which is equal to 7.9, which is equal to 7.9, can be approximated into 8 meter per second. 8 meters per second. All right, a man covers the first 240 meters of his journey at a speed of 4 meters per second, and the second 240 meters at a speed of 10 meters per second along a straight line. Compute his average velocity. Average velocity is the total displacement upon the total time taken. I told you average is about every of the movement, is about every of the motion. It considers all of the motions at once. Now let's have a diagram. It covers the first 240 meter of his journey at a speed of, let's say this is the first 240 meter of his journey. He covered it at a speed of 4 meters per second, and then the second speed, the second, his second journey, which is at 240 meter per second, 240 meter, he covered it at a speed of 10 meters per second, and is of course along a straight line. Now how do you compute his average velocity? The average velocity has to be the total displacement. The total displacement is 240 meters, and then 240. So we have 240 plus 240 in meters. In order to find the total time taken, we get to find the time covered from this point, let's say t1, and the time covered from this point, let's say t2. Okay, now to find t1, that means the velocity here, or the speed in which is 4 meter per second, has to be equal to the distance upon the time that is taken. So the we can make this t1 the subject of the formula, which will become t upon v. Then the distance covered is 240 meters upon the velocity that is being covered, that's 4, so which is 60 seconds. Since this is in meters and this is in meter per second, so meter cancels out meter in order to give us second. So it took the man 60 seconds to cover his 240 journey. So that's 60 seconds plus, okay, then the other time, which is t2, has to be equal to the distance, which is 240 upon the speed, which is 10, and this is in meters, this is in meter per second. So the meter cancels out meter, so that we'll be left with 1 over, the unit in this case is just like dividing m divided by m upon s. So in this case, if m cancels out, then we'll be left with 1 upon 1 over s. So it is like 1 divided by 1 upon s, which is the same thing as 1 multiplied by s upon 1. So it gives us s eventually, and that's why we have s here. So in this case, we'll be left with 24 seconds. As a result, we have 24 seconds. This is in meters and this is in meter. So eventually, we'll have something of this nature. 480 meters upon, that's 84 seconds. As a result, 5.7 meter per second. The implication is that for every 1 seconds, it covered 5.7 meters. So that's the implication. Acceleration is the time rate of change of velocity. That is acceleration A. It is the time rate of change of velocity v minus u upon t. Let's say a bicycle rider moves at initial velocity of u from point A and then to point B, where its final velocity is v. So the acceleration in this case is the change, the time rate, that is the final velocity minus the initial upon the time, this will give us the acceleration of that object. Now the instantaneous acceleration is the acceleration at an instant, at a particular instant. It is also the limiting value of the acceleration when change in time tends to 0. That is, if a body accelerates from point A to point B, we can find the acceleration at a particular instant in time. And in that case, the time interval will be very, very small compared to the whole journey. As a result, the limiting value of the acceleration, the instantaneous acceleration, is equal to the limiting value of the change in the velocity upon the time when the change in time tends to 0, when the change in time is very, very small. This expression can also be represented as dv dt, where v is the velocity. But don't forget that velocity is the same thing as ds dt, where s is the distance, that is the time rate of change in the displacement, where v is the velocity or speed. So in this case, we can say that dv dt will now become instead of having v, we will have ds dt. So this can be represented as, that means we are differentiating the s dt the second time, so that's going to be d square of ds upon dt squared. So this is the where s is the distance or the displacement. So given a particular displacement, we differentiate twice in order to get the acceleration, but given velocity, we differentiate once in order to arrive at the instantaneous acceleration. So it implies that acceleration is the second derivative of displacement, or the first derivative of the velocity. Let's say the motion of an object is described by this equation: s equal to at plus bt squared, where a is 0.2 meter per second, b is 4 meter per second, s is the distance in meter, and t is time in second. We can find the displacement between the time interval of, let's find the displacement between the time interval of, let's say, 3 seconds and then 6 seconds. So in order to find the displacement between this time interval, we will substitute the value of t. Let's say this is t1 and then this is t2. We will substitute the values of t at the different position in time. Now, since s is in meters and then we know the value of a which is 0.2 meter per second, and then t plus b which is 4 meter per second, okay, and then t squared. Okay, so at 3 seconds, the value of s will become 0.2 multiplied by 3 plus 4 multiplied by 3 squared. 3 squared is 9, so we'll have equal to 21.6 meters. Now at 6 seconds, the distance will be equal to 0.2 multiplied by 6, then plus 4 multiplied by 6 squared, which is 36, so that we'll have something of this nature. That will be 1.2 plus 144, which is supposed to be equal to 145.2 meters. So the displacement between the time interval t1 and t2, let's say this is s1 and then this is s2, between that time interval, that will be s2 minus s1, which is 145.2 minus 21.6, and of course that will be equal to 108.6 meters. All right, now let's say we want to find the average velocity in that interval. The average velocity in that interval is the total displacement in that interval upon the total time in that interval, will be equal to the total displacement and that interval. The total displacement at the interval is s2 minus s1, and the total time at that interval is t2 minus t1, and of course that is 108.6 upon minus 3, and of course that is 108.6 upon 3, which is equal to 36.2 meter per second, where meter per second is the unit of velocity. Let's say you want to find the instantaneous velocity of that particle at a time which is 5 seconds. So the instantaneous velocity, which is instantaneous velocity, which has to be equal to the limiting value, the limiting value the limiting value of the change in the distance upon the change in time. And don't forget that this expression can be replaced by ds dt. and of course dt, and of course we'll have to differentiate the s, that is we find the derivative of s, which is this equation. So if we find it with respect to time t, if we find the derivative, which is the s dt, and it has to be at a particular time t, which is 5 seconds. Okay, so the derivative of s, the first derivative of s will be, if we differentiate at, it will become a plus, if you differentiate bt squared, that will be 2bt. Okay, this is the basic definition of differentiation. Let's say that you have an equation y equals to ax raised to power n, then you can find the y dx. The y dx is, you bring down the n, then it should be multiplied with ax, then you subtract 1 from the power. So you bring down the old power, then you subtract 1 from the old power to form a new power. So I have just done the same thing here. I brought down 2 and then subtract 1 from the power, which is 2 minus 1, so that eventually we'll have a plus 2bt. Now at time t equals to 5, then the equation will become a plus 2b multiplied by 5, which is equal to a plus 10b. It is that a is 4, so that we'll have, okay, a is 0.2, so that we'll have 0.2 plus 10 multiplied by b, where b is 4, so that's 0.2 plus 40, and of course that will be 40.2. This is the instantaneous velocity, and then the unit will be meters per second. So 40.2 is the velocity of that object, of the particle, at that instant where t is equals to 5 seconds. If you didn't get how I differentiated this at, it's just basically, if s is equal to at, then we can find ds upon dt, which will be, the power of t here is 1, so that's 1 multiplied by at1 minus 1. You subtract 1 from the old power to form a new power, so that we'll have at upon 0. And notice that according to law of indices, t raised to power 0 becomes 1, so that we'll have a, and that's why this is a. To find the instantaneous acceleration at 5 seconds, don't forget that the instantaneous acceleration is this. Let's find the second derivative of s with respect to time. If we find ds dt, that will be equal to a plus 2bt, and then the second derivative, which is d square s dt squared, that will be, a is a constant, so it becomes 0. It becomes 0 because a is similar to at raised to power 0, and of course if you differentiate this, that is 0 multiplied by a t raised to power 0 minus 1. 0 multiplied by all of this becomes 0, so, and that's why this is 0 plus this is 2bt raised to power 1. If we differentiate, that is 1 times 2bt raised to power 1 minus 1, so it becomes 2b t raised to power 0, and of course t raised to power 0 is 1, so it becomes 2b. So this is 0 plus 2b. Notice that b is given as 4. As a result, we have 8 meter per second squared. So let's say the position of a particle is described by this equation, and then you want to find the time at which the particle is at rest. The time at which the particle is at rest is the time at which the instantaneous velocity of that particle is equal to 0. Okay, so that means the instantaneous velocity, which is ds dt, we want to find the time at which this will be equal to 0. Given s as this, then ds dt ds dt will be equal to a minus 2bt equal to 0. So we get to solve this equation to obtain t. So if we take t to the other side, it becomes minus 2bt, which is equals to minus a. By dividing both sides by minus 2b in order to obtain t minus 2b, then t has to be equal to a upon 2b, since minus cancels out to obtain positive. Notice that a is 0.2 and then b is 4. So that implies that 0.2 upon 8, and of course that is 0.025 seconds. So that's the time at which the particle will be at rest.